Imagine the sun suddenly vanished. Earth wouldn't immediately fly into deep space. It takes about 8 minutes to feel the change in gravity. This delay exists because of a rule called locality. In physics, effects spread from place to place at a hard maximum limit, the speed of light. Cause must always come before effect, and there is no such thing as instant action over a distance. Albert Einstein figured this out in 1905. He realized that Newton's old assumption of instant gravity led to impossible paradoxes, where observers moving at different speeds could see an effect happen before its cause. The speed of light acts as the structural integrity of reality. The delay between an event and its consequence guarantees that everyone in the universe can agree on the order of events. But when physicists started looking at the smallest microscopic pieces of matter, that structural integrity suddenly seemed to crack. The theory of quantum mechanics proposed that particles like electrons don't exist in one solid place. Instead, they have a wave function, a spread-out wave of pure probability. As you see in this animation, the wave spreads through space right up until the exact moment you measure it. When you finally detect the particle, it registers at a single point, and the rest of the probability wave instantly drops to zero everywhere else. To Einstein, this was a disaster. If a wave function stretches across miles of space, and measuring one end instantly collapses the other, then the particle is communicating with itself faster than light. He called it spooky action at a distance. At the 1927 Solvay conference, Einstein took to the stage to challenge the other architects of quantum physics. He argued that this instant collapse violated the strict rule of locality he had built general relativity on. The physics community was left at a crossroads. Either the mathematics of quantum theory were missing a crucial piece, or the absolute rule of cause and effect was broken. In 1935, Einstein and two colleagues published the EPR paper, offering a logical way out. They looked at entangled particles, pairs whose states are permanently linked. Einstein suggested these particles must agree on what they are going to do before they separate. We can visualize this idea, known as local hidden variables, with a simple analogy. Imagine two particles seal their predetermined answers, say a plus and a minus spin, into envelopes while they are still touching, before flying to opposite ends of the universe. Under this theory, when you measure a particle, you just open your envelope. The distant particle doesn't need to receive a faster-than-light message to know what to do, because it already had the opposite answer packed away. The argument was elegant, but Niels Bohr, the leading voice in quantum mechanics, rejected it. In a famously dense rebuttal, Bohr essentially argued that asking what particles are doing before you measure them is a meaningless question. For the next 30 years, the physics community sided with Bohr. They treated Einstein's concerns about locality as a philosophical distraction, choosing to use the math that worked rather than worry about the logic hiding underneath. That complacency ended in 1964 when a physicist named John Bell decided to look closer at Einstein's forgotten envelopes. He realized you could construct a mathematical trap to prove whether those hidden variables actually existed. Here is a diagram of how that trap works. Instead of measuring entangled particles in just one direction, experimenters independently rotate their measurement devices to ask the particles different questions, specifically along three distinct axes, 0, 120, and 240 degrees. Bell mapped out every possible combination of pre-written answers the particles could parry in their envelopes. He found that if you randomly choose different measurement axes, the local strategy requires the particles to disagree on their results at least 33% of the time. But standard quantum mechanics predicts something entirely different. The equations say that the particles' states remain completely undecided until measurement, resulting in a disagreement rate of exactly 25%. The debate was finally testable. Over the following decades, scientists, building on early entanglement experiments by pioneers like Chien-Shiung Wu, ran the numbers in real laboratories. The disagreement rate always landed at 25%. The particles failed to produce the answers required by the envelope theory. Einstein's local hidden variables could not explain the data. The results forced the scientific world to accept that distant particles really do influence each other across the universe instantly. The success of Bell's theorem left physicists with a deeply uncomfortable reality. Bell had turned spooky action at a distance from a mathematical debate into a verified physical law. Accepting instant connections across space shatters the clean, orderly timeline defined by relativity. If observers moving at different speeds disagree on the order of events, an instant influence in one frame of reference looks like an effect preceding its cause in another, a timeline running in reverse. This deep contradiction might explain a massive roadblock in modern science. For decades, physicists have tried to unite the gravity of large objects with the quantum behavior of small ones, consistently failing because they are trying to stitch together a local theory of gravity with a strictly non-local quantum world. But there is one final, radical way out, a mathematical loophole that preserves the speed of light, provided you are willing to accept an entirely different version of reality. Bell's proof rests on a single assumption, that when you measure a particle, you only ever get one result, either a plus or a minus. Here is a visualization of an alternative idea, known as the many worlds interpretation. Instead of the probability wave collapsing into a single outcome, it never collapses at all. Instead, the universe splits into two parallel paths, one where you measure a plus and another where you measure a minus. In this scenario, the faraway particle doesn't need to instantly transmit its status across empty space. Both answers already exist in the two separate timelines. The information travels forward locally without ever breaking the speed of light. Parallel universes are often dismissed as science fiction, but they represent a rigorous mathematical requirement. They offer the only known way to reconcile quantum mechanics with the universal speed limit.